Started here. So it's great to have Dr. Emily Levesque here. She's been visiting us from the University of Washington. So she got her PhD in 2010 for the University of Hawaii. Then she was an Einstein Fellow and then a Hubble Fellow, both at the University of Colorado Boulder. And then she joined the faculty at Washington in 2015. Oh yeah, I hope it's along the way, she's won some impressive awards. So she got the Amy Johnson Prize through LAS. She's also currently a Sloan Fellow right now as well. And she's an expert in massive stars. So she's improving our understanding of them both locally and in the early universe, and we're going to hear more about it today. So thank you.
Hi. So thanks again for having me here. As mentioned, I'm Emily Levesque from the University of Washington. If anybody knows a quick solution for how to fix this, that would be excellent. Do you happen to know if this happens more if it's HDMI or if it's VGA?
Don't know.
Because I have
contagious among these things.
What are you using now?
Right now I have VGA or Thunderbolt connected to HDMI because my actual HDMI port does not work. So I may try doing VGA. But while I do that, it's okay if I disconnect.
Yes.
Okay. Yeah. So while I do that, I can at least start talking about why my talk has the title it does. Because the title is Red Supergiants as a Magnifying Glass for Stellar Theory. And this is actually a quote that I stole from Kippenhahn and Weigert. So I don't know how many of you know their classic 1990 textbook on stellar. Yeah. So in there, they're talking about why it's interesting to model massive stars and the things that you can learn from modeling massive stars. And in there, they actually specifically call out evolved massive stars. And it's almost back. Yeah. Cool. So hopefully this now cooperates. But they're describing evolved massive stars in particular, and they describe them as a magnifying glass for evolutionary theory, quote, revealing relentlessly the flaws in the calculations of earlier phases. And this is why I'm interested in red supergiants in particular. They represent a very extreme evolved phase of massive stellar evolution, and as a result, they're one, really cool, literally, and interesting in their own right, and they serve as really valuable tests for a lot of what we understand about how massive stars work. So as I go through this, I'll also be pointing out work being done by some of the people in my research group at the University of Washington. So this is our massive stars group. It includes Emily Levesque, who is a postdoc at UW now. She's getting ready to start a faculty position at the Naval Academy in the fall. Grad students Trevor Dorn-Wallenstein and Kathleen Nugent. And then undergrads, Locke Patton, so he is about to head to grad school at Harvard, and Rick DeCenzo, who actually started working with me as a high school student and is getting ready to transfer to UW from a community college in Eastern Washington. So a lot of their work relates to red supergiants or massive stars or supernovae in some way, so I'll be highlighting it as it goes along. So to start off, I always like to start by looking at the Hertzsprung-Russell diagram and reminding people of where we're working. So if we populate the HR diagram with a normal sample of stars, we are all very familiar with the main sequence and with stars that are about the mass of our sun that will eventually evolve off the main sequence, turn up the red giant branch, maybe turn back to become horizontal branch stars, become HEV stars, and then disappear. Those are not at all what I'm talking about. One of the unfortunate things about red supergiants is that their names sound almost identical to red giants. These are two very different evolutionary pathways, and I want to very much highlight that these are the ones that we're talking about. So red supergiants are the evolutionary consequences of massive stars. These are maybe 10 million years old as opposed to 10 billion years old, and they're evolving horizontally across the HR diagram from stars that start with a mass of 8 solar masses or more. So to walk through this, we define red supergiants as being the helium-fusing, very evolved descendants of moderately massive stars, so from about 8 to 40 solar masses on the HR diagram. So if you start with a 15 or 20 solar mass star on the main sequence, it will go through it will go through hydrogen fusion, and then at some point hydrogen fusion will cease. As this happens, it will, following the basic rules of how luminosity goes as radius squared and temperature to the fourth, begin to cool off while maintaining an almost constant luminosity. So it evolves horizontally on the HR diagram. It makes a very brief pit stop as it crosses the HR diagram as a yellow supergiant. This entire crossing takes maybe 100,000 years, so this is a short moment in the life of the massive star. And it eventually ends up over here as a red supergiant. So these red supergiants are the coldest and physically largest massive stars that we know about. They are The radii can get up to something like 2,000 times the radius of our own sun. They're very distinct from red giants. They have higher initial masses, shorter lifetimes. Their evolutionary pathway is very different, as I already mentioned. And they're either an end phase or an intermediate phase in massive star evolution. So sometimes a star will simply die and explode as a red supergiant. This will be the immediate progenitor of something like a type 2P supernova, which I'll talk about more later. In other cases, this will be an interim phase in the star's life, and as it sits here fusing helium and eventually fusing heavier and heavier elements, its outer layers will begin to be shed. It passes back through that brief yellow supergiant phase, and eventually winds up like off the slide somewhere over on the left side of the room as a very hot Wolf-Rayet star. So these are the two basic endpoints that we can get after something has been a red supergiant. We either see a direct supernova explosion, or we see it evolve into another stage, usually a hotter stage, of massive star evolution. If we trace all of that out, we wind up with a typical massive star evolutionary track. I just sort of did this as a cartoon example, but you can assemble a full set of stellar evolutionary tracks on a theoretical HR diagram. Looking at all of this, you can immediately get a sense of what the exteriors of red supergiants are going to look like. Whether we start at 12 solar masses, 15, even going all the way up to 40 solar masses, there's a very narrow and very distinct temperature range where red supergiants will fall. So these are about 3,300 to 4,500 Kelvin.
My bad.
It's okay. We can still see it. They're about 3,300 to 4,500 Kelvin in temperature. So this is what they look like on the outside. What I always try to connect is what we're seeing externally for red supergiants versus what we're seeing internally. So this is what the interior of the star has been doing over the course of its life. If we look at a Kippenhahn diagram for this star, and if you haven't seen Kippenhahn diagrams, they're showing mass fraction on the y-axis and time on the x-axis. We're, in this case, modeling a 15 solar mass star starting from its birth on the main sequence, where we're fusing hydrogen into helium in a convective core, and the hydrogen fusion zone here is shown in red. As we switch from fusing hydrogen to fusing helium, we wind up with a helium fusing core, and then eventually a helium fusing shell shown in blue, and a hydrogen fusing shell around it. It is this point on the Kippenhahn diagram where something becomes a red supergiant. So while we're having a red supergiant rave, and while we're having a small light party and also watching the star expand into a cold massive star, this is what's going on in its interior. There's something interesting about how the interiors actually connect to the exteriors. We're going to have a star dance party to go along with the lights, because the interiors of these stars have those massive convective zones that you saw in the Kippenhahn diagram. That convection zone size and the scale height and density of the convection zone mean that we have very large convective cells that reach from very deep in a red supergiant up to its surface. It means that the surface of a red supergiant is both cold and variable. Because if you take this case, which is a simulation of a sort of Betelgeuse-like red supergiant, and watch what happens to the surface, this is what convection is doing at the surface of a red supergiant. The star basically looks like it's boiling and almost deforming. You see very noticeable bright spots and cold spots, changing and varying on pretty rapid timescales when you consider how massive this star is. This is what's connecting what's going on in the interior to what's going on in the exterior of the star. And the main question that I find interesting here is what this winds up doing to the photometry of the star and the variability of it. So all of this was meant to give a sort of general intro to what red supergiants are, what characterizes their observed appearance, what their interiors are doing, and how we sort of connect these. The question that I always try to answer in a talk like this is, who cares? They're neat, they're cold, they're massive stars, but who actually cares about red supergiants? Why are they important? I maintain that you do, and that everybody in here cares about red supergiants in some way. If you are interested in any type of stellar evolution at all, we need to understand red supergiants, both to model massive stars and to understand things like supernova production and enrichment of stars in the early universe. If you are interested in stellar populations, say in other galaxies, you want to understand how the red supergiants are doing things like contributing to the dust fraction, or contributing to the luminosity of the galaxy over in red. If you're interested in gravitational waves, these are the stars that are the progenitors of things like neutron stars and black holes. So there are a broad number of applications for red supergiants. I'll come back to a few of these at the end, but I just wanted to start out by emphasizing how important these stars are to a really wide swath of astronomy. With that in mind, something I'd like to highlight next is some of the challenges involved in studying red supergiants, because they're big cold stars, that's really neat, but there's a lot about them that we need to understand if we're going to effectively use them as magnifying glasses and as cosmological tools. So one of the first challenges to understanding red supergiants is understanding their temperatures. I showed this plot before, and I highlighted the very narrow temperature range where red supergiants exist. To the right of this is a region of the HR diagram that I think a lot of us are familiar with. So this is the sort of forbidden region to the right of the Hayashi limit. The Hayashi limit is what is dictating the temperature of red supergiants. It's effectively an opacity effect that we're seeing in the atmospheres of cool stars that is telling us how cold a star can appear to be while staying in hydrostatic equilibrium. If we were to plot stars on the HR diagram and they were to land here, this would be an immediate signal that something was wrong. It suggests that the stars are not in equilibrium, that they are disobeying the Hayashi limit for very hard to understand reasons, or that our theory is wrong. About 15 years ago, if you were to take observations of red supergiants in the Milky Way and drop them on this plot, that's exactly where they would land. They would be in a region of the diagram where stable stars shouldn't be able to exist. These data were based on observed brightnesses and observed temperatures for red supergiants. Their positions seemed unarguable, so we all naturally immediately blamed the theorists. And went, well, your tracks are clearly wrong. They need to move farther into the cold part of the HR diagram. It's obviously something that the theorists are doing wrong. What ultimately got sorted out, and what wound up being my very first REU project, because this is from some research I did midway through college in 2005, was that the observations of red supergiant temperatures were what was actually off. This is an example of a red supergiant spectrum, and in this case it's a model spectrum produced by the Marx Stellar Atmosphere Group in France. What we can do is evolve this spectrum and see how it changes as we go from something like a 4,000 Kelvin red supergiant, which would have a spectral type of K1, to a 3,500 Kelvin red supergiant, which has a spectral type of M5. As we do that, you notice that these very big, broad molecular absorption bands show up in the star. So these are the titanium oxide absorption bands. We all know these as tools for spectral typing, K and M type stars. In red supergiants, which are very young and very short-lived, these are direct temperature gauges. We're not seeing abundance changes or abundance effects or age effects nearly as much as we're just seeing the direct consequence of the star getting colder. So as you go from 4,000 Kelvin down to 3,500 Kelvin again, those titanium oxide bands get incredibly strong. Until the Marx group put out their like early 2000 version of these models, we weren't able to use these as temperature diagnostics. We were doing things like roughly estimating the star's colors and assuming that they were black bodies, or taking red giant effective temperature scales that would map spectral type to temperature and just sort of shifting them down by a few hundred Kelvin. So my very first project was taking these spectra, fitting the depths of titanium oxide bands in observed red supergiants to the depths of model spectra, and remeasuring a bunch of temperatures. And when we did that, the positions of the red supergiants moved from here to here on the HR diagram. So the theorists were right, the observers were wrong, our interpretations of the temperatures were off, and we seemed to have now perfectly solved this question of what red supergiant temperatures are. So we're done, right? There are still a few problems with this. This method starts breaking down in low metallicity galaxies. If we look at low metallicity evolutionary tracks and low metallicity atmosphere models, the agreement starts to get less perfect, and we still wind up with some red supergiants that sit on the wrong side of the Hayashi limit. This technique is also very limited to optical data. The titanium oxide bands go from about 4,000 to 9,000 angstroms. In the infrared, the data doesn't quite match up. If I were to extend that Marx model into the infrared and compare it to an actual observation, you wouldn't see a perfect matchup. There's also the good point that getting spectra are observationally costly. So a lasting question is, are there other ways of trying to measure these temperatures? Could we do it with very broadband SED fitting, even taking into account that the atmosphere models aren't perfect? Could we use some other technique to mass examine temperatures of red supergiants? Could we possibly even do it without broad spectra, but with spectra of very narrow regions like the calcium-3 triplet, things that are captured by Gaia spectra? So these are all open questions for how we can measure lots of red supergiant temperatures and how we can get better at it. Along these lines, I want to go to another challenge of how we study red supergiants, and this is looking at red supergiants in other galaxies. What we would love to do is get great observations of extragalactic red supergiants to measure temperatures and how they vary with metallicity, to measure luminosities, to get a sense of the population studies, to identify stars that could explode as supernovae. It's one of the key appeals of studying red supergiants because they're so luminous that they're easy to capture in other galaxies. But we need to start by identifying them and then actually getting some sense of what their physical properties are. So, where do we start? They are red supergiants, they're red and luminous, so an obvious first step would be, if we want to identify red supergiants in other galaxies, we pick the red things. We pick some color cut and say everything redder than this is likely to be a red supergiant. Even picking that color cut is difficult because the range of temperatures that we're looking for depends on the galaxy that we're looking in. I showed you that Hayashi limit before, that rightmost limit that dictates how cold a star is allowed to be while staying in equilibrium. The Hayashi limit actually shifts to warmer temperatures as we go to lower metallicities. The plot that I have on the screen now is another theoretical HR diagram, and it shows Milky Way evolutionary tracks in black, LMC tracks in red, and SMC tracks in blue. So as you go from solar metallicity in the Milky Way to LMC metallicity, so about half solar, and then to SMC metallicity, about 20% solar, there's this clear shift to warmer temperatures in the Hayashi limit. Where this actually comes from is the idea that you have more free electrons at higher metallicity. This leads to a higher abundance of H-, so this is the main opacity source in cool star atmospheres. The opacity goes as T to the 9th. This is a proof that I love doing in my grad stellar interiors class, where you actually prove that this temperature starts becoming, or luminosity starts becoming completely independent of temperature, and it's why you get that vertical line. But that shift does depend on the opacity source, and as a result depends on the metallicity. So what this means is that stars that are in low metallicity galaxies actually cover a different range of spectral types and a different range of colors. So we've seen this observationally in a couple different cases. This is a set of histograms of red supergiant spectral types going from K0 to M5, going from the Milky Way, so about solar metallicity, down to the Wolf-Lundmark-Melotte dwarf galaxy in the local group, which is a 10th solar metallicity. The spectral type distribution period goes from about mid-M to early K as we go to lower metallicities. So we're directly seeing a consequence of the titanium oxide bands getting weaker and of the stars themselves getting warmer. Maria Drought actually also observed this when she was observing red supergiants in M33. So what's shown here are a single set of evolutionary tracks and red supergiants that are being plotted in M33 as we go from the outskirts of the galaxy, where the metallicity is fairly low, to the interior, where the metallicity is fairly high. And you can watch the red supergiants move as we go from the exterior to the interior. The red supergiants actually get colder. They drift from fairly deep inside the outer limit of the evolutionary tracks to aligning perfectly with the limit. So we've observationally seen this shift. What all of this comes out to is that this means there's a warmer average effective temperature for red supergiants at low metallicity, and it means their average color is bluer. So if you were to pick a particular B minus V or V minus R as a color cut for red supergiants based on Milky Way red supergiants, you would lose a huge amount of the population in the Small Magellanic Cloud or in WLM. You'd be missing the orange supergiants, the stars that are evolutionarily at the same point, but are simply warmer because of the effect of metallicity. So even deciding what red means, if you're looking for these stars in other galaxies, starts to get hard. Supergiant, deciding what luminosity you want to look for, also starts to get really messy. You'd like to pick a range of luminosities. Basically, on the right side of the HR diagram, a range of masses that we want to look for when we call something a red supergiant. If you just look at sort of the cartoon HR diagram, this looks really easy. You just go to that cutoff line of 8 solar masses and you draw a line and you say, we're done. Everything above this luminosity is a massive star. Everything that's above that luminosity in red is going to be a red supergiant. And this works really well because you do capture the red supergiants very satisfactorily. But you also capture something like a super AGV star or an unusually luminous red giant. going all the way down to 8 solar masses means you start capturing the very tip of the giant branch, and you get contamination in your sample from stars that are also red and luminous, but that represent a totally different evolutionary state. Trying to avoid this is actually really difficult. You can look at the full distribution of, in this case, some galactic red supergiants on an HR diagram, and try to decide where you want to put your luminosity cut. You could put it down here and capture all of the red supergiants, but you're almost certainly going to get some AGB stars. You could put the cut very high and guarantee that there is no AGB star contamination, but because of the IMF, this is also wreaking havoc on your completeness. If you're missing the 12 solar mass and the 10 solar mass and the 8 solar mass red supergiants, you're missing most of the red supergiants. So just taking a really conservative cut is bad if you want to get a complete sample in another galaxy. We kind of hand wave our way to about this cut for now. We'll look at a log L that's about 4, so 10 to the 4 solar luminosities or more. It's an okay compromise. We are definitely still losing some of the lowest mass red supergiants. So one of the things that I'm actually really interested in trying to do is finding easy diagnostics for distinguishing between a red supergiant and an AGB star. This is so far proving to be very difficult photometrically. It's even hard to do spectroscopically unless you get really good spectra and look at very specific diagnostics, which I'll show in a second. But yeah, so red is a hard value to choose, and luminous red supergiant is a hard value to choose. We also have other parameters that can affect what we see as the red supergiant luminosity range. We need distances to be measured very accurately. If you are just a little bit off in terms of what the star's luminosity is, remember, temperature is constant, so on the HR diagram, varying luminosity moves you directly up and down. You could easily delve into the super AGB star range or start losing stars that are very luminous if your distance measurement is even a little bit off. Metallicity is also expected to affect this. It is predicted that maximum luminosity for something like a red supergiant should be metallicity dependent. Now, we've actually had several papers over the past 10 years or so showing that we don't see this. And it's a bit puzzling as to why that is. What it really reveals is that we just don't have a good understanding of what metallicity is doing to maximum luminosity for stars like this. Circumstellar dust also causes a big issue. This is a red supergiant, somewhere in there. This is the red supergiant BY Canis Majoris, which is surrounded by a massive dust reflection nebula. That's causing a huge amount of extinction. We have a number of other red supergiants that we know are partially enshrouded by dust, that are strong dust producers, that are sporadic dust producers. So if we can't account for the circumstellar dust effect, we could easily lose massive red supergiants that are just producing a lot of dust and effectively hiding themselves from a simple photometric survey. We also know that these stars are really photometrically variable. Even a normal red supergiant varies by up to a magnitude in V. Some of the unusual ones vary by several magnitudes. The most extreme one that I've seen varies by something like 5 magnitudes in V. So that kind of degree of variability will really mess up trying to select a luminosity that's appropriate for finding a red supergiant. Yeah?
What's the time scale of that variability?
Depends. There's actually long period variables that they vary slowly over the course of a couple of years. There's shorter periods where they vary on the time scale of months. There's cases where this variability does not look periodic at all. It appears to, for lack of better study, be random. But it can impact observations that are taken as little as a couple months apart. So all of this winds up impacting what we would choose as a luminosity cut or magnitude cut for studying red supergiants and other galaxies. We also have lots of contaminants to consider. Looking in the direction of something like the LMC or M31 and just saying everything bright and red is a red supergiant is very incomplete. You'll get an enormous population, especially for big galaxies, of foreground dwarfs. They also look luminous, they also look red, we are simply getting their distances wrong. There's a couple good ways that we can tell the difference between these. One of them is actually this diagnostic, which Phil Massey first developed back in the late 90s. And what it does here is it plots red supergiants, which are colored in red, and then a small sample of them that we observe spectroscopically are in blue, and red dwarfs, which are in black, on a color-color diagram. So in this case, it's B minus R versus B minus B. What you're actually seeing is an effect coming from the differences between the high surface gravities of dwarfs and the low surface gravities of supergiants. You're actually seeing really different line widths in the blue and different amounts of line blanketing. So that winds up separating the stars on these plots, and the blue supergiants actually wind up on top. Sorry, the red supergiants actually wind up on top. So if you have this kind of photometry, you can immediately separate them in that manner. You can also do this kinematically a little bit. You can try and get good senses of radial velocities and proper motions for foreground dwarfs versus background supergiants and see if that can help you distinguish between the two. Foreground giants is a little bit harder. That photometric effect starts to disappear. So in that case, you can again try to use kinematics, see if what you think is a background red supergiant really does agree with the motion of its host galaxy. You can also try other diagnostics for measuring surface gravity. The calcium-2 absorption triplet over about 8,500 angstroms is fairly surface gravity sensitive. It's also sensitive to things like metallicity and temperature, so it's not a perfect diagnostic, but you see it get narrower as you go to higher surface gravities. We actually recently found that the same thing happens for H-alpha. There is a small but present H-alpha line in even very cool star spectra, and it goes from being very broad in supergiants to very narrow in dwarfs. So if you have the advantage of something like a shell spectra of a bunch of stars, or a very focused spectra of a bunch of red stars on H-alpha or on calcium-2, you can use this to distinguish even between supergiants and giants. The problem is that sort of data is very expensive and relatively rare.
That goes backwards from simple stellar hemispheres. Can you explain why it's going backwards?
Yes. So the reason we're seeing this happen in H-alpha, it actually comes from, let me make sure I get this right. It comes from the metastable 2s level in a hydrogen atom. It winds up getting overpopulated in any of these stars. In a high density star, that overpopulation will quickly be collisionally dispersed, so you wind up with a relatively narrow line. In a supergiant, the overpopulation is allowed to persist, so you wind up with a much broader range of transitions. The geometry of the line is also really weird. It's not a void profile, it's not quite Lorentzian. We're actually still messing with why the geometry looks the way it does, but it's counter to what you would normally expect of just collisional broadening, because in this case it's collisional removing of things from the overpopulated level. Did that make sense? It is counterintuitive. The calcium-2 line does the same thing, but for a very different reason. In the case of calcium-2, it appears to get stronger in supergiants, not because the line itself is getting stronger, but because the continuum opacity is changing. The continuum opacity starts to decrease in a supergiant, so the continuum rises and the line appears to be deeper. But they always bother me because both of them go backwards to what you would expect. So Brooke DeCenzo, so this is one of my students, I'm highlighting all of their names in purple, thanks to UW's colors. She is working with me on an in-prep paper where we're trying to look for other surface gravity diagnostics and other temperature diagnostics in red supergiants beyond just those titanium oxide bands. And what we're hoping for is that we can disentangle things like metallicity effects, temperature effects, and surface gravity effects and get better at telling the difference between something like a giant and a supergiant. The final contaminant, which is surprising but very important, is background galaxies. A lot of times when you're just looking for a bright red thing, you will wind up with something like an elliptical galaxy. We can usually tell the difference between a red supergiant in another galaxy and a background galaxy by getting deep result imaging because the galaxy will wind up looking fuzzy, although red supergiants can sometimes look fuzzy as well. Sometimes the only way we can do this is by actually getting spectra. So this data point right here looks like a red supergiant in the outskirts of M31. This was actually found by Trevor Dorn-Wallenstein, who was a graduate student working with me, when we were trying to find red supergiants in X-ray binaries. We had an incredibly sophisticated way of doing this. We looked at bright red things and we looked at X-ray bright things and tried to see what lined up. This object had appeared in people's catalogs as a red supergiant. Maybe a couple people thought it was a red giant, but it was very much classified as stellar. And we went after it to get a spectrum, thinking we'd found the first red supergiant companion in an X-ray binary, because none has ever been spotted before. And this was the spectrum that we got, and I didn't recognize it when I first looked at it, because I haven't worked on galaxies in a very long time. I was tilting my head going, I want to make this into a titanium oxide band, and we can almost make it work. What it actually is a very red, low luminosity AGN. So you're seeing the very broad quasar lines. If I'm remembering correctly, its redshift was it was 0.215, it's very nearby. It's also intrinsically red. This isn't a consequence of reddening from M31. The galaxy is actually this red. We had some really interesting follow-up of it. We've got time-resolved photometry. The time-resolved photometry wound up having a period in it. This was partly why some people had typed it as a star. We tentatively think that what we found is a good candidate for two supermassive black holes in a binary in this low luminosity AGN, because we see periods in a perfect 4-to-1 resonance. It's very surprising. We came across this completely by accident. We would love to do more follow-up of it, but it was a great example of something that we thought was a red supergiant turning into something else entirely. So all of these are challenges that I've laid out for how it's difficult to look for red supergiants in other galaxies. Coming off of this are other things that we want to understand about these stars. We would love to understand more about red supergiant mass loss. We know that these stars shed an enormous amount of mass over the course of their lifetimes. They sometimes shed mass sporadically. We don't see steady winds from these stars. You see signs of circumstellar dust shells around them. You see signs of eruptions from stars like this. And we really have a weak understanding of what drives that. A lot of times you'll see dust-driven mass loss invoked, which is what's typically invoked to explain red giant or AGB star mass loss. But that's not quite enough here. You need dust at a very close radius to the star, and we're not quite certain that we're accomplishing that. Line-driven mass loss isn't necessarily enough because of the complexity of the lines in these stars' atmospheres. People have invoked alpha wave mass loss or pulsationally driven mass loss. But none of these are perfect on their own, and we don't know what combination is dictating what's happening. For now, all we can really do in an evolutionary track is kind of fake it and turn on extreme mass loss at a certain point in their evolution. So this is a 20 solar mass star's evolutionary track shown in black. And at the little white point here, this was modeled with just normal mass loss, which is the black track that behaves exactly as we would expect it to for a red supergiant. 10 times the usual amount of mass loss, which is shown in blue, and 25 times the normal amount of mass loss, which is shown in red. And it does really different things to the star. It starts to turn it into a yellow star again. It changes its luminosity very drastically. It changes its entire evolution on the HR diagram. This is interesting because when we capture red supergiants in something like pre-supernova imaging, we're catching them at the dead ends of their lives, just before they produce supernovae. So if we detect a star here or here, and don't account for something like mass loss, we'll infer its mass wrong, we'll infer its evolutionary state wrong, and it starts to cause all sorts of problems. So knowing what is causing the mass loss and what it winds up doing to the star's evolution is really valuable. It even winds up impacting the star's color, because if a red supergiant winds up with a thick dust cloud around it, you sometimes see the dust behaving as a sort of reflection nebula. We actually see this even in relatively garden variety red supergiant spectra. So this is an observed spectrum in black and a model spectrum in red. And what you see over here is this weird excess in the blue from what turns out to be a dust reflection nebula around the star. We looked to see if this could be a sign of a companion, but we don't see nearly enough of a turn-up in the blue for this to be something like a B-star companion that you would expect for a red supergiant. So that dust reflection winds up impacting things like their UV luminosities and the colors of these stars if you're trying to select them in color samples. We're trying to actually take a kind of unusual approach to tackling this and to understanding what their circumstellar mass loss is coming from. This is an image that I've stolen from exoplanet people. This is an image from GPI using the GPI coronagraph, so this is the Gemini planet imager, to identify, in this case, planets around a small parent star. What we're actually trying to do, just in the past couple of years, is sort of steal GPI from the planet hunters and point it at red supergiants. So this is an image that Jamie Lomax took, she's the postdoc working with me at UW, of a very garden variety red supergiant. We purposely wanted to do a pilot study with a supergiant that we thought was very typical. Not dramatically dusty, not dramatically unusual. The star itself is blocked out behind the coronagraph, but you can see asymmetries in the dust in general, and what appears to be a dust clump on the southern end of the star. This is GPI H-band data we actually just got. We just downloaded, I think, a month or so ago. STIS observations of this. STIS on Hubble has a chronographic bar, and what we're trying to do is get optical photometry of this as well. What we're hoping to do is that we can get color information about the circumstellar environment around this star, figure out what the nature of the dust is, figure out where the asymmetry is coming from, and hopefully use this as a springboard to observe a bunch of red supergiants like this and try to better understand their circumstellar environments. As a bonus, this is also a really good way of sometimes finding small companions around these stars. So I've been talking about mass loss invoked directly from something like line-driven winds or dust-driven mass loss or pulsations. There's also another very obvious way that stars can lose mass, and this is from binary interactions. So binary interaction or binary mass loss will dramatically impact how red supergiants evolve and how they die. The evolutionary tracks that I have on the screen right now are from J.J. Eldridge's VPAS models. They go from 10 solar masses up to 60 solar masses. In this case, they're modeling the evolution of just single stars. What I want to compare this to is the evolution of a star in a typical binary system. So we're modeling what the primary is doing in this case. And this is taking a relatively typical mass range. These are 10 solar mass stars with 1 solar mass companions, 15 solar mass stars with 1.5 solar mass companions, and relatively wide binary radii. So eventually when the stars hit their largest radius, you will start to see the effects of mass loss. The red supergiant gets stripped, it cools off. They actually wind up producing a large population of Roche lobe-stripped Wolf-Rayet stars. And this is what you expect just from a typical binary evolution. If you grab extreme binaries, cases where the mass ratio is closer or the binary radius is closer, that interaction winds up happening very early on. It happens almost as soon as the stars leave the main sequence and start to expand. And it has a huge effect on how the star evolves and what the star looks like when it winds up dying. So understanding the binary fraction of red supergiants and understanding the fraction of them that are in interacting binaries is incredibly important. Trevor Dorn Wallenstein is actually, he's the student who wound up accidentally discovering our periodic AGN, is actually working on a project now that's looking at the population implications of binary evolution, looking at how many Wolf-Rayet stars you would expect to see, how many red supergiants you would expect to see, how many yellow supergiants you would expect to see, as the binary fraction changes and as metallicity changes and as we consider sort of the full parameter space that you could play with when you're looking at red supergiants and binaries. Another nice way to do this would be to simply try and go out and observationally count the red supergiants that we see in binaries. What's surprising is that we know very little about these systems. We have maybe a dozen red supergiants that we know have binary companions, and none of them are actually in interacting binaries. I think the most famous one on this list is VV Cephei. So this is an M2 supergiant and a B3 dwarf that's orbiting in the wind of the star. So it's orbiting fairly close, and it is interacting with the wind from the star, but it is not an interacting binary. That companion is not pulling mass off the red supergiant. It's sort of picking up what the red supergiant already put down from mass loss. This particular binary happens to be eclipsing, so we get some really nice observations of the B star as it's sort of emerging from the star's wind before and after eclipse. We have a few other examples of stars like this. Another great example is Zeta Aurigae. I put it on there just for fun to put it at scale. So this is an M2 supergiant, that's a K-type supergiant, and a little B star companion orbiting it. If you blow it up, you can see that it's, again, a very similar system. But again, we have a B star orbiting far out in the wind of a K star. In this case, the B star actually completely emerges, and you're able to see it fairly nicely when it's at outer points in its evolution. But trying to identify more systems like this is very difficult, and they seem to be very rare. The kind of classic prediction is that all massive stars should be in binaries. This is the number that we hear thrown around. And they should all be in interacting binaries. So interaction should have a massive impact on every star's lifetime. What's surprising is that that should be happening at the red supergiant evolutionary point. These are when the stars are at their physically largest. This is when they should be overflowing their Roche lobe. This should be the exact point at which we start seeing interacting binaries. And the fact that we see very few is really puzzling. There's a couple different arguments as to why. It could be that those companions are being obscured for some reason by the dust that these stars produce. We could have tons of red supergiants and binaries where we simply never see the companion. It could be that our estimate of the binary fraction is off, that there are fewer companions or the companions are at very wide distances where the interactions actually aren't happening. But it's hard for us to know until we actually do the experiment. So this is work, I had her name on the previous slide, but this is work that Catherine Nugent, another graduate student of mine, is working on. She's working on modeling and predicting what binary systems with red supergiants and B stars, or red supergiants and O stars in them, would look like, and whether we can identify them photometrically or observationally. What we're trying to understand is, out of the red supergiants that are in binaries, which ones are in detached binaries, where they're orbiting one another, but the two stars are very distinct and not bothering one another. These are the ones that we see. whether they're in things like semi-detached binaries, where you have some mass loss happening from the primary, or whether we even see red supergiants in contact binaries, so binary systems where the two stars are enveloped, where you're basically sharing a common envelope and where the interaction between them is going to be severe. We haven't seen any red supergiant so far in semi-detached binaries. I mean, I would say that we haven't seen red supergiants in contact binaries. This is not quite true, because we have seen what we think is an example of a sort of extreme consequence of red supergiant contact binary evolution. So this is a Thorne-Jitgov object. So what Thorne-Jitgov objects are a theoretical class of star where we have a neutron star core that's surrounded by a large diffuse envelope. These were predicted by Kip Thorne and Anna Jitgov back in the 1970s. It's thought to be a stable model for how massive stars can work. And the only way that we can think of to actually make one comes from binary evolution of two massive stars. So one idea is that you have something like a OB main sequence star and a neutron star in a binary, and then when the OB star evolves into a red supergiant, the red supergiant's radius gets huge, it swallows the neutron star, and the neutron star spirals into the core. So you would have to invoke semi-detached and then eventually contact binary evolution. The other idea is a collision scenario. So in this case, you have two massive stars where one has produced a red supergiant and the other has died and produced a neutron star. In this case, the supernova velocity kick of that neutron star actually sends it flying into a companion. It sounds ridiculous. It sounds like you have to have a supernova with like awesome aim. But when you think about the angle that that red supergiant is subtending, it's actually not that unusual to imagine that you could send a neutron star flying into or past or very close to a red supergiant companion. And either way, we start with the binary and wind up putting a neutron star at the heart of a red supergiant. The difficulty with these for a long time, and the reason that they stayed theoretical stars for 40 years, was that Thorne-Jitgov objects should look exactly like red supergiants. It's a cold envelope that would appear as 3,300 to 4,500 Kelvin. And we shouldn't be able to tell the difference between a normal red supergiant and something with a neutron star embedded in its heart. Almost. The key difference can come if you get really high resolution spectra of the cool star and look for chemical signatures of that neutron star at the core. So what I have here is a sort of PowerPoint drawn cross-section of a red supergiant. And this, in this case, is a normal red supergiant. You have the surface, you have those big convective regions that I showed you in the animation earlier, and then you have the helium-fusing core. If you transition from a normal red supergiant to a Thorne-Jitgov object, you now have a very cold red supergiant where the entire envelope is completely convective, and deep in the star, a neutron star core. The trick here is to think about what's happening to a packet of material in the envelope of a Thorne-Jitgov object as it's being convected. Convection speeds in these stars are sonic, even supersonic in some cases, so the rate at which material is being convected through the surface of the star is very fast. A packet of material will get dragged down to this region near the surface of the neutron star core, and in that region, the temperature and pressure, the temperature and density are so incredibly high that protons are basically being pushed onto the nuclei of atoms in that material. So these things basically start undergoing what's called the rapid proton process, and they start getting slammed up the periodic table. The material only stays in this part of the star for about 1/100th of a second, and then it gets dragged back out into cooler regions of the convective envelope. When it gets there, it starts to undergo beta decay, but the beta decay does not last very long before the material is dragged back down and gets bombarded with protons again, and the whole cycle continues over and over. This actually produces something known as the interrupted rapid proton process, and it's a process that should only happen inside a Thorne-Jitgov object because of this geometry. So it gives us things like excesses of molybdenum and lithium and rubidium at the surface of the star, and none of these are elements that we're like purposely going after in normal red supergiants. So it's a little bit hard to say what an excess of molybdenum would look like in a red supergiant. I've been working on red supergiants for about 10 years when I got an email from Anna Jitgov saying, I think you might be interested in these stars that Kip Thorne and I predicted. Have you ever thought about going to look for them? And what we did was go back to a series of red supergiants that we'd already observed with moderate resolution spectra like this, and got very high resolution shell spectra. We did this for a sample of about 70 stars. And what we were trying to do was identify the molybdenum line, the lithium line, and the rubidium line in normal red supergiants with the intent of establishing a baseline. We wanted to basically say, well, this is what normal molybdenum looks like, So if you want to go looking for a Thorne-Jacob object, here's where you should start. We tried to pick our sample in the hopes that maybe something in there was going to be a TZO. I don't think we really had terribly high hopes. But out of our 70 star sample, 69 of them looked like this, and one of them looked like this. We had one star that had a massive excess of molybdenum, much more rubidium than you would expect, and much more molybdenum than you would expect. We did all of these as ratios, so we were looking at the molybdenum to iron ratio, or lithium to potassium, or rubidium to nickel, doing ratios to elements that shouldn't be enhanced in a TZO. So we had one star that wound up perfectly fitting our profile for what we would consider a Thorne-Jacob object. So we now have what we think is the first candidate for a star like this. We would love to find more. This is something we're actively working on. We're considering new techniques of finding them that maybe don't involve getting a shell spectra of 70 stars, because that's very costly. But this is, the technical standard of astronomy. One object is an oddity, and when you have two, you have a class. So we're hoping that we can get a few more of these and actually start to understand what these mean for massive star evolution and what this means for even how we understand how stellar interiors can work. I have how long left? About?
Oh, 5-10 minutes.
5-10 minutes, perfect. Okay. So the last thing that I wanted to touch on was going back to my Uncle Sam Wants You recruiting slide for red supergiants, of who cares about red supergiants and why we find them interesting. I have a bunch of reasons listed here, and I can cover all of them. But I specifically want to look at 3 in particular, and these are gravitational waves, supernova progenitors, and studies of strange and variable stars. So gravitational waves feels like it's been thrown in here gratuitously, but I very much think that red supergiants are crucial if we want to understand gravitational waves. This isn't just a line in the talk from the past year and a half because of LIGO results. Something like the colliding neutron star system has evolved from a red supergiant in a binary. We have 1, possibly even 2 stars that were red supergiants when they died. These stars for sure passed through a red supergiant stage of their evolution. So understanding how the stars lose mass, how they interact in binaries, how they explode, what they look like when they explode, all of this winds up directly affecting what the neutron star binary system is going to be. If we know more about how the stars lose mass, if we know more about what their binary fraction is and what that implies for the frequency of colliding neutron star systems, if we know what their evolution does to their core collapse and whether they make a neutron star or a black hole, this all helps us to understand gravitational wave evolution better. Their role as supernova progenitors themselves I also find really interesting. We see red supergiants as direct supernova progenitors, and you can see an animation of it here. So this is a pre-supernova image from Hubble, one of the only ones that we have in this really nice color image of supernova 2008 BK. So this is pre-supernova, this is post-supernova. You can see in that case very obviously that there was a red supergiant, and now there is not. So that red supergiant has definitively disappeared and shown us that it is the direct progenitor of what we discovered as supernova 2008 BK. So direct progenitors are fairly well established. They've also been mapped in every case where we've detected a red supergiant progenitor to a type 2p supernova. So if you're not super familiar with all of the supernova subtypes, and there's a new one something like once a month at this point, type 2p is a big cluster. If you watch the evolution of this supernova's light curve with time, you will see the peak, a plateau in the light curve, and then a drop-off. So that plateau is being interpreted as an interaction between the supernova's shock wave and the very thick envelope of the red supergiant. So the shock wave is basically ionizing the outer envelope layers and giving us a temporary constant radius, almost opacity effect, before continuing to disappear. So understanding the outer layers of red supergiants and understanding how they lose mass, again, really helps us to understand and interpret something like a supernova light curve after one of these stars dies. It's also really important to understand where a star dies as a red supergiant versus where it may make a pit stop as a red supergiant before evolving back to the blue and exploding as something like a Wolf-Rayet star, which is a supernova progenitor that we've actually not directly seen yet. We have one good candidate for a Wolf-Rayet star dying and producing a supernova, but we would expect to see many more, and we're trying to understand why we don't see as many as we do. This plot right here is actually comparing evolutionary tracks shown in solid lines, dashed lines, and then dotted lines of stars that are single but very rapidly rotating, or stars that are in binaries. Overplotted in gray are all of the red supergiant supernova progenitors that we know well enough to put on the HR diagram. Trying to translate from that dot to an exact progenitor mass is pretty messy if you look at how much these evolutionary tracks overlap. Adopting a non-rotating star versus a rotating star versus a binary star dramatically changes where something like a 12 solar mass red supergiant might wind up on the HR diagram. So taking a data point like that and trying to back solve to a mass, which we would love to do to understand pre-supernova evolution, gets really messy if we don't know more about red supergiant evolution and which of these evolutionary tracks we should be adopting. Yeah, sorry, that's what that arrow was meant to indicate. Before I keep going, I actually want to highlight one small thing about supernova light curves that we're working on right now at the University of Washington. So I showed you an example of a type 2p supernova. It's one of the supernova types that can be very easily identified from its light curve. We're actually in the very early stages of a project that I'm calling Transient Zoo. So it's a citizen science project that's meant to help people quickly and easily classify supernova light curves. We can do this with our eyes. We can look at that and say, oh, it went up, it plateaued, it went down, that's probably a type 2p. Or if something goes straight down, it's a type 2l or a type 1a or something like that. What we're actually trying to do is develop an auditory light curve classification system. We can translate what we see in a plot as a change in brightness into a change in pitch, with brighter things having higher pitches and dimmer things having lower pitches. It means that you can listen to this light curve and it winds up sounding something like this. You can hear the plateau. If you play that same sound file for a type 1a that just drops straight down, or a type 1l, you don't hear a plateau. It's a very different evolution of pitch. What we're working on is a citizen science project that can actually be used by people who are visually impaired, which is something that we don't yet have in astronomy. What we want to do is put it into something like a mobile-friendly platform. There's no way for me to describe this without making it sound like Tinder, but swiping in one direction if you identify it as a plateau, swiping in another direction if you identify it as linear, swiping up if you think it's something very bizarre. And very bizarre has sometimes led to some really fun classifications in citizen science. Yeah?
If you have a type 1a supernova that's pretty slowly declining, the R-band light curve's going to look just like this.
Yes, we noticed. So one of the things that we need to do is control for time. We obviously didn't play this in real time, and controlling for what the time range of the data is and whether you're seeing a short plateau from a type 1a or a lengthy plateau from a type 2 is something we need to be able to control for. You also don't want to give somebody a sound file that's too long to listen to. You're not going to sit there for 10 minutes listening to so we're in the early phases of developing this right now. We're actually getting ready to work with speech and hearing sciences at UW to test this with people. The idea is that ultimately we can use this with ZTF data and eventually LSST data when we wind up with hundreds of thousands of light curves. Right now we're working with transients. We'd like to expand this into light curve zoo where you can also classify variable stars, listen to our Lyrae variable versus a Cepheid and hear the differences there. So it's in very early stages. This is something that Locke has been working on in his spare time. His actual research project is looking at supernova host sites, but it's something that I hope will have a lot more to show people in the near future. So this last point, briefly, is the applications of strange and variable stars to red supergiants. We know that these stars vary photometrically. I mentioned that some of them vary by at least a magnitude on as little as a timescale of months. They also vary spectroscopically. So these are 4 spectra of one red supergiant going from 2004 to 2013. It changed from a K-type star to an M4 type star to M2-ish to M3-ish. We really don't have a good explanation for why the star is doing that. And we're trying to understand what mechanisms dictate red supergiant variability. You'll see things like that large-scale surface convection that I showed before. Radial pulsations in the star. We know that some of them are pulsators. There's sporadic mass loss and what that does to the star's surface, what that does to the star's opacity, and what it does to its perceived temperature. How the circumstellar dust changes around the star. Things like hydrostatic instabilities, which we know that some of these stars should have. What binary companions do to their photometry and to their spectroscopy, and other effects that we really haven't even honed in on yet. So all of these things are aspects of red supergiant variability that we'd like to understand more. We have a lot of new tools that are going to be amazing for this. JWST and this slide was a lot happier like 2 months ago. JWST and WFIRST are both going to be excellent for studying red supergiants, in part because of their focus on IR. We'll be able to identify local and extragalactic red supergiant populations. We'll get massive surveys that let us stock up piles of what could be pre-imaging of supernova progenitors. And we'll be able to look at their mass loss and their dust production in a lot more detail. Things like the extremely large telescopes are also going to be excellent tools for this sort of stellar astrophysics. We can get spectra of extragalactic red supergiants, so individual stars out to something like 50 megaparsecs. The adaptive optics imaging that we'll be able to do of really distant red supergiant samples will also be incredible. As we get better at things like photometric diagnostics, we'll be able to learn way more about these stars and other galaxies. And then finally, LSST is getting ready to usher in a completely new era of transient astronomy. So this will be great for studying core collapse events from these stars, supernovae, or even these cases of disappearing red supergiants, where a red supergiant forms a black hole directly and just winks out of existence. We've seen what looks like one of these events in NGC 6946 recently. LSST will be great at finding more. It'll also be great for variability in red supergiants before they even die. We'll have really good light curves of them and hopefully be able to get a better understanding of what is dictating their variability. So all of this is part of something that I want to plug, and part of the reason that I've been spending so much time on red supergiants over the past couple of years. I wrote an ebook on the astrophysics of red supergiants. It was published as part of the IOP-AAS ebook series. This is not a blatant plug because I don't get paid. The ebook is free if your library has a subscription to IOP. And if you want to hear about these and other aspects of red supergiants, it's a very short book. They gave me a few print copies, so it's 100 pages. It's very small. It's meant to be at the advanced astronomy grad student level, basically for somebody who is interested in red supergiants but isn't specializing in them. It should offer a complete primer on what we know about red supergiants right now, so if you do think that these are interesting and something you want to learn about more for your research, I can highly recommend using the book as a reference. So on that note, thank you very much, and I'm happy to take questions.
Are there any questions?
In the run-up to Betelgeuse having a supernova explosion, the neutrino flux ought to increase quite a bit. If we don't have sensitive enough neutrino detectors to measure that, how else might we know it's going off really soon?
So there are some people that are specifically trying to model what the evolutionary track is going to do in the last few years of its life. When we put up evolutionary tracks, we like to pretend that they're complete. Most people stop at carbon fusion. There's people that are trying to model what those 2 days of silicon fusion will look like, what oxygen fusion or neon will look like near the end of the star's life. And also trying to accommodate things like gravity waves propagating in the star and what that does to them. There's Jim Fuller at Caltech has done some work on this, and if you look at his evolutionary tracks on the HR diagram, they look hysterical because they look like modern art. The evolutionary track is just doing this. Like, it's to the point where it would actually be very difficult to observationally interpret. I think even he admits there's probably a lot of knobs and dials that are currently being turned that we need to firm up before it means anything, but we can try and estimate what the death throes of a star like that would look like, and whether what's going on in the core would manifest to stuff that we can see at the surface.
It's been a long time since I worked in this field, but the real bugaboo in all of this were the radii of these stars. So are the radii well known at this point, so you can really put them in the theoretical plane? Or, because you have the effective temperature, which is difficult to interpret in a star like this.
Yes.
And also the radii, the past was the radii, because there were very few occultations of red supergiants. So can you tell me about the work that's been done on the radii?
Yeah, we still don't have a great grip on the physical radii. A lot of times we'll take the effective radius and say that that's the radius, but obviously the interaction radius should be larger. If anything, that actually makes it more surprising that we're not seeing interacting red supergiants, because most of them should be bigger than they look, and you should expect to see more interaction. What people are starting to get better at is interferometry of these stars, and we now have some interferometric radii for red supergiants. You'll see results coming out of like the Chara array, where people have an image of, was it Arcturus that it was Arcturus or Antares that they did very recently. One of them was a red giant and one of them was a red supergiant, but they actually get a disk estimate of it. The problem is most of these are still too far away for even that. I'm hoping that something like really good coronography could at least help put outer limits on the radii. But in terms of measuring the physical radii, we don't have great tools for that right now. And from the interaction perspective, I'm kind of happy starting with the effective radius and saying that is a minimum, And if we're seeing, maybe we'll see interaction in a star and realize that that is implying a radius larger than what we're seeing. But I think until we detect a system like that, we're stuck saying effective radius and sticking with the few interferometric results that we have.
And the effective temperature is coming from photometry or from spectroscopy?
Spectroscopy at this point. And the effective temperature itself is actually funny because in the atmospheres of these stars, the opacity or the optical depth is wavelength dependent. So the effective temperature in the optical and the effective temperature in the IR are two different things. There have been some papers in the past few years that are trying different techniques for measuring the effective temperature. So far, our technique of using the titanium oxide bands is still the best one. It actually very nicely reproduces things like the Hayashi limit shift, which things like IR photometric temperatures or atomic line temperatures are barely able to do. But I think we need an answer that's satisfactory across multiple wavelengths because the optical effective radius is even less precise than the effective radius period. So some of that is getting better 3D atmosphere models that can account for the wavelength-dependent effects. Some of that is getting more IR observations because these stars are surprisingly understudied in the IR for how IR bright they are, and hopefully those will improve with time. Other questions? Yes?
So the lower the metallicies, it does affect the overall color in the sense that it makes it bluer. So I'm just wondering, the models that you scored, that are scored, how low metallicity do they usually go?
I think the lowest metallicity atmosphere models that we're using right now are about a 10th solar. So
They're lower than that?
I'm sure that people have run one-off models that go lower, but the current grid, looking at grids of something like the Marx models or the Phoenix models are another set that sometimes get used. The Marx models I know don't go below a 10th solar. And the Phoenix models, I don't know that they even go that low. Partly that's because that's the observational sample that we have. The lowest metallicity red supergiants that we can observe right now are in things like the Wolf-Lundmark Galaxies, or we have a sample right now that we're working on in the sextants, and those are like 7 to 10% solar. It would be great to go lower, but I haven't seen something like population synthesis done with a 100th solar metallicity red supergiant population.
There's some groups who use lower metallicity, but the main reason why I'm asking is because these things are, wolf-radiated stars and such. These are very high redshift words.
Yes, they are.
So and in particular, we know high redshift metallicies, at least for very, very young starbursts, are well below 10 solar. So,
oh yeah.
So I'd like to understand a bit better how that would affect the information we get.
Yeah.
In terms of reconstructing the solar populations and systems.
To give a more complete answer, the model atmospheres don't really go below about a 10th solar that I've seen them use. The evolutionary tracks definitely go way lower. There's people that will model very low metallicity evolution, but we don't yet have observations of low metallicity red supergiants to like test them. So this is the plug that I always put in my grant applications. These are our local analogs to high redshift massive stars. So if we can get observations in the sextants, beyond the sextants, and like other really low metallicity galaxies, then we can at least try and test the evolutionary tracks. But until then, we're flying a little bit blind with how accurate those are. Yeah.
Has anyone, following on that, has anybody looked at 1 week E18 for supergiants?
Oh my God, I would love to.
Is it too far?
It's too far right now.
Oh yeah.
This is sitting on a sticky note somewhere in my office with a little note saying, please do this math. But I think it would be possible to capture either individual red supergiants or at the very least clusters of red supergiants, because we tend to see them in clusters, and a cluster spectrum would still be informative. With the ELTs, I believe. But crowding starts to become a massive issue, even with as amazing as you can get with adaptive optics, there starts to become a physical limit. But yeah, I would love to look at ones with E18. Yeah?
If you look at the energetics of a massive star going from birth to death, the actual amount of light that's produced in fusion is negligible compared to gravitational energy. Almost everything that comes out of the star over its lifetime comes from gravitational energy, which gets turned into neutrinos at the very end. So I don't quite understand how you can take a neutron star and put it into the center of a red giant. Where does all that energy go? Because that's a huge amount of gravitational energy. It's got to go somewhere. So
yeah.
That would seem like you puff the star up, there'd be a sudden increase in luminosity. Where does that energy go?
Yeah, this is one of the main things that we're debating right now about thermal top objects. That the interior model that suggests that they're stable, and I won't get the details right now, now, but it's basically invoking very slow gravitational accretion on that neutron star at the core, combined with very slow emission. So obviously, if it could accrete at speed, it would last seconds, and this would never become a stable model. Combining very slow accretion with very slow emission means that you can get to a stable model for that, but we still don't know how long an object like this would live. And there's sort of two competing schools, and one is that the lifetime is actually dictated, like you said, by raising the luminosity and puffing up the star. In this case, I think the estimate is these would live like 100,000 years or something like that, and the star would puff itself apart. And what it would leave behind is a sort of naked neutron star that's been dramatically braked and is rotating very slowly because of what has happened to it as it moved into the center of the red supergiant. There's actually a group that thinks they found one. They found a very slow rotating neutron star and pointed to possible previous TZO evolution as an explanation for that rotation. The other model is that you would actually have the lifetime limited by the neutron star eventually dying as a black hole. But the accretion rate is expected to be so slow that that would take on the order of 1 billion years. So if the star is not puffing itself apart, and I personally think it's pretty likely that they puff themselves apart first, if that did not happen though, you would wind up with a billion-year-old apparent red supergiant waiting for the neutron star to eventually die as a black hole. And those interest me because the way we would find them is to look at something like a globular cluster and look for an unusually bright, unusually red, and unusually luminous member. So something like an AGB star that looks way too bright for the cluster. And there actually are a couple stars like this in clusters that we're getting spectra of. But they're sort of two competing models of what is dictating TZO lifetime, and it gets back to how they would be able to stay stable. So hopefully we'll get some observational data to distinguish between the two, but until we do, I think we can only speculate.
What I was saying was it's not the stability of the object once it forms. It's going from the neutron star on the outside to the center, which is a huge amount of gravitational energy.
Yeah, the
and so
neutron
that
star
process produces lots and lots of energy, and it's not coming out of neutrinos like it does in the core collapse scenario. So you're dealing with a huge amount of energy dumping it somewhere.
Yeah.
So that,
you're talking about the gravitational energy produced during formation and during the decay of the binary. So this is a question I've asked some people, is whether you would see an observational signature of formation, that maybe you do see something supernova-like, or you do see some flare or some means of releasing that energy. I've talked to people that think that that formation should have a gravitational wave signature, which doesn't solve the question that you're asking necessarily, but it would be great if we could catch one of these forming, or if we knew what sort of transient event their formation produced, because they should produce something. You shouldn't just have a neutron star quietly spiraling in and nothing happening. We don't know whether that would look like a supernova, like some sort of high energy or high energy transient that we haven't seen before. We just don't have a good sense yet. I don't think anybody's modeled them yet.
well, as supernovae, apparent supernovae are staying bright for 2 or 3 years.
Yeah.
It did not fit nickel 56 and iron 56
Yes.
Supernova explosions. So
Yeah.
there are things that are really weird out there.
This is
That somehow
IPTF,
maintaining high luminosity.
Yes, this was IPTF 14D, but I can't remember the letters. But it's invoked, the idea was that it used to be a red supergiant too, and people are trying to explain what is going on, and I have to admit that when I was reading about it, I was wondering if we were seeing TZO formation or something that could be explained by a TZO, because it appears like the death of a red supergiant, but with some oddities baked in. Yeah. Any other questions? I know we're like way over time.
Save one for later.